All right, we're going to solve problem 2.3. Find the electric field at distance z about one end of a straight line segment of length L. This figure, 2.7, that carries a uniform line charge lambda. That's the linear charge density. Check that your formula is consistent with what you would expect for the case when z is much greater than L. Okay, let's do this. So what we have is a line segment. So let's call this x-axis. This is my origin. This is x equals L. And this is my z-axis. And this is my field point P. Okay. So this is a continuous charge distribution. So between x equals 0 and x equals L, I have lambda linear charge density. Okay, so lambda is uniform linear charge density per unit length here. Now, essentially, we are doing exactly the same as what we did for discrete point charges. But in this case, since we have an infinite charge distribution along a line, I would say it is finite, but I can make infinitely many point charges between 0 and L. I'm going to chop this up, right? I'm going to chop this up into many, many pieces. And to represent one of them, I'm going to say, okay, let's say at coordinate x, right? This is my coordinate x. I picked a tiny segment, this segment of length dx. So this is x plus dx, basically. Okay, x plus dx. And this has a charge amount of dq, infinitesimally small charge amount of dq. So this is my point charge, but I have many, many of these. I'm chopping this up into infinitely many segments. So I have one here, one here, one here, one here. So I need to add the contribution of all these infinitely many point charges to the field at point P. So for this segment dq at coordinate x, this is my script r vector, right? Because this is my source, this is my field point, and this is my separation vector, script r. Now, the field point, again, I can write its coordinates, 0, 0, z. So I can say, all right, r, that's the field point, is z, z hat. The source point is always on the x-axis, and its coordinate is represented by, right, this is x, 0, 0. So if I write r prime, in this case, it's going to be x, x hat. So the separation vector then, script r, would be r minus r prime, and script r would be z, z hat minus x, x hat. Okay, so this is what I need to use in setting up my integral. Well, for linear charge distributions in this section of the book, we see, okay, now we have ER 1 over r squared r hat dq. That's what I need to integrate. And for a linear charge distribution, this is what I have, lambda dl prime, right? dl prime, in this case, dx, basically. And that's what I need to integrate along this line segment from x equals 0 to x equals L. So E of r is 1 over 4 pi epsilon naught. Integrate 1 over script r squared dq script r hat. Okay, now dl prime, which represents the sources along this line, in this case is dx. So dq dx defines my linear charge density lambda. So instead of dq, I can substitute lambda dx. Right, this goes here. Now script r vector is here, and as I can repeat, r hat, script r hat is basically script r vector divided by script r cube. So I can write this as z hat minus x hat divided by, this is the magnitude of this, obviously, x squared plus z squared. Right? You can see here too, this is x, this is z, x squared plus z squared. And square root, if I raise it to the third power, I'm going to get x squared plus z squared 3/2. Okay. Now, instead of r hat over script r squared, let me make sure this is correct. This is r hat over r hat over r squared. I can put r over r cubed, script r over script r cubed, magnitude cubed, and this is what it is. So I can now plug that in. Okay, so er then 1 over 4 pi epsilon naught integrate, instead of dq, I have lambda dx, and then I have z hat minus x hat, all divided by x squared plus z squared 3/2. Okay, so what's remaining here, basically doing two integrals, one for the z component, one for the x component, and that will do the job. Okay, so I can write this in two separate integrals, one for x, one for z component. So lambda over 4 pi epsilon naught, and then I can say, all right, I need to have minus x hat integral. Again, the integration limits is x equals 0 to L. This one is also x equals 0 to L. And then here I have minus x hat x over x dx over x squared plus z squared 3/2. And then I have plus z hat integral x 0 to L. Then I have z dx over x squared plus z squared 3/2. I could have taken that z out of the integral because the integration variable is x. Okay, so I have two integrals to evaluate here. The first one is very easy. I can just do a u substitution. X squared plus z squared is u, and x dx can be expressed in terms of du, and then you can evaluate that. And the other one could be a little more challenging. You need some trigonometric substitution here. Okay, now once you set up this integral, actually the rest is just this integration, and you can do that in different ways. I mean, you can, if you want to do from scratch, you can do that, or if you want, you can look up in an integration table, or I'm going to show you how to do these integrals in Mathematica. Okay, so we can enter these integrals in Mathematica, we can immediately get the results. So let's do that. All right, as you see on the screen, I'm going to use the integrate command. Integrate, open square bracket, close square bracket, f comma x gives me the indefinite integral f dx. That's what I want to do. So that's what I'm going to use. So integrate. Now, my first function here is x over x squared plus z squared to the raised to the 3 halves. Okay, so control 6, that's going to give me that subscript x squared plus z squared. Okay, this is my function. And then I'm going to say, okay, comma x, and that should do the integral for me. All right, this is what it is. I'm going to copy that over. Lambda over 4 pi epsilon naught minus x hat. Now I have minus another minus, so it's going to become plus 1 over root x squared plus z squared, evaluated at 0 and L. And now I want to do the other integral. Okay, so the syntax is very similar. I'm going to just make a little bit of change. In this case, I have z here. Okay, z over x squared plus z squared 3 halves, again, dx. All right, so I'm going to take that, and this is my integral plus z hat x over z square root of x squared plus z squared, and again evaluated from 0 to L. All right, that's how you would do it in Mathematica. All right, let's finalize it. Here now I'm going to evaluate these. Lambda over 4 pi epsilon naught x hat. Now at L, I have 1 over L squared plus z squared square root, minus at 0, I have 1 over square root of z squared, plus z hat, and at L, I have L over square root of L squared plus z squared, minus, and then I have 0. This, it makes this entire thing 0. Right? So this is what I have. So I have, as a result, E of R is lambda over 4 pi epsilon naught and x hat 1 over root L squared plus z squared minus 1 over z plus z hat L over square root of L squared plus z squared. Okay, that's going to be my electric field. Now, the last part of the question asks, verify if this formula approaches the correct solution when we are sufficiently far away from this line of charge. Meaning, if z is much greater than L, so what do we expect? Well, if you are really, really far away from this, again, pause this for a moment and think about it yourself. If you're really far away from this, you would see it like a point charge, right? If you are really, really far away. So if z is much greater than L, then the entire charge, a total charge of, say, Q is going to be lambda times L, right? This is line charge per length, a total length of L. This is the total charge. So you can just use Coulomb's law, and what you expect then, E of Z at far away distances, right, should be something like 1 over 4 pi epsilon naught lambda L total charge over Z squared. And you expect it to be in the Z direction, because you are so far away that if this is a little bit to the right, a little bit to the left, that doesn't matter anymore. So this is, you know, some point charge almost at the origin. So you expect something like this. So let's see if this is going to give that. So if you are sufficiently far away, then we should look at each of these functions for the x component and for the z component, and in the limit, when you have L over Z going to 0, what value they're going to approach. Okay, so that's what we're going to do. So the x component, I just copied over. I want to see what happens to it when Z is much greater than L. So what I can do is I can just factor out this Z squared here, just to show that very clearly. So I have 1 over square root of Z squared, 1 plus L over Z squared. Okay, and then minus 1 over Z. Now what do I have here? This can be taken out, and this is L over Z. So then if L over Z goes to 0, EX, well, if this goes to 0, so what I'm left with is essentially 1 over Z minus 1 over Z, right? And that's 0. So it approaches 0. The x component is going away. Let's look at the z component. So EZ is lambda over 4 pi epsilon naught L over square root of L squared plus Z squared. Well, it's a similar thing, right? I can do the same factorization here and write this as lambda over 4 pi epsilon naught, or lambda times L over 4 pi epsilon naught, and then 1 over square root of Z squared and 1 plus L over Z quantity squared, all under square root. Now again, I'm going to look at limit when L over Z goes to 0 of EZ. Then I would have lambda L over 4 pi epsilon naught. And then here, this L over Z approaches to 0. I think I copied of something incorrectly. I'm just noticing it. I just corrected it. I had one Z here. I forgot to copy it over. So there's another Z here, another Z here. So there's a Z here and then a Z here. Okay. So that's Z, and then take the square root of Z squared. I have a Z squared. And then the rest is basically 1 over root 1 plus L over Z squared. Again, this term goes to 0, and this is 1. So the rest will be 1 over 4 pi epsilon naught lambda L over Z squared. Again, that's what we were expecting from Coulomb's law, right? Only Z component survives, X component goes to 0, and that's what we expect. Lambda L is the total charge, and 1 over Z squared, that's the distance from that point charge when you're looking from really far away, and that's exactly what we expect. So our relationship here works, okay? Except I forgot to copy over this Z when I was writing these few lines and then evaluating it here for the limiting behavior. All right, I hope you enjoyed the solution.